We want to talk about one special case of antiderivatives. We remember the general rule for antiderivatives that says, recall that if you have a function f of x equals x to the n, remember x is going to be your variable, n is going to be the power on your variable, it represents a constant here. For little f of x equals x to the n, the antiderivative given by capital F of x, it's given by x is now raised to the n plus 1 power, and in front of that is a constant, 1 over that new power, 1 over n plus 1, and then plus c for that arbitrary constant. Now this rule held as long as n wasn't equal to negative 1. So for example, if we had for, let's say, f of x equals x to the fourth. Okay, and then we remembered that the antiderivative of that, capital F of x, we would take the exponent, which is currently 4, we would add 1 to it to get 5, and then in front of that we would get 1/5, and then we would add the arbitrary constant. And you can always check, because when you take the derivative of this antiderivative, you should come back to x to the fourth, and in this case you do. It worked for, it didn't have to be a positive exponent. We could say f of x equals x to the negative 3. Well, in that case, your antiderivative, you'd do the same thing. You add 1 to the negative 3, but you'd get negative 2. And out front, you'd get 1 over negative 2 and add your arbitrary constant. And you could, of course, rewrite this. You don't have to, but it's 1 over 2x squared plus c. So this rule for antiderivatives works as long as n isn't equal to negative 1. Because if you let x be equal to negative 1 and you try to use this rule, watch what happens. If you add 1 to the negative 1, what's going to happen is you're going to get x to the 0 power. Now already I know something is wrong, because x to the 0 is just 1. In other words, this would have no variable in it. But the other problem is, watch this, if you put the constant out front, it would be 1 divided by the new power, which is 0, and that's a big giant no-no. So the question we would then ask ourselves, how are we supposed to find the derivative if that exponent is negative 1? If we have f of x equals x to the negative 1, also known as 1 over x. What is the antiderivative of this going to look like? So before we actually answer that question, let's think about a couple things. We remember that the derivative of the natural log of x is 1 over x. And given the relationship between a derivative and an antiderivative, you might be inclined to say, okay, well then if you have little f of x equals 1 over x, then its antiderivative must be the natural log of x plus c. And the good news is we're on the right track. But there's a problem. See, when we talk about antiderivatives, like we did on the previous slide, they're supposed to hold for any legitimate x. Well, given that this one contains a natural log, what are the values of x that we would allow as inputs into this? Well, since it's a log function, remember its domain is 0 to infinity, not including 0. So you can't take the log of 0 and you can't take the log of a negative number. Well, notice that's not the same as the domain of f of x, the original function. 0 is out of its domain, so they have that in common. So I'm not worried about x equal to 0. But for this original function, x is supposed to be able to be negative, and in its antiderivative, it's not. So that causes a problem for us. In order to kind of examine what that's going to do, we want to take a look at another problem. So let's take a look at the derivative with respect to x of the natural log of the absolute value of x. And what you want to keep in mind in order to take care of this is that the piecewise definition for absolute value of x, it's equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. That's by definition what we mean by absolute value. I'm going to leave out the or equal to in this example just because I've already said neither one of these have 0 in their domain, so I'm not worried about 0. But what I do want to do is say, okay, well, since I'm now taking a derivative involving an absolute value, this would be equal to one of two things. It would be equal to the derivative of the natural log of just x, if x is greater than 0. I'm using the piecewise definition without the equal to. And it would be the derivative of the natural log of the opposite of x if x were less than 0. Again, using that piecewise definition. Okay, so when we take each one of those derivatives individually, we already know the derivative of the natural log of x, that's 1 over x. So the derivative is 1 over x if x is greater than 0. In order to take the derivative of the natural log of the opposite of x, notice your input now has a function in there, not just an input of x, which means we're about to use chain rule. So that's 1 over your inside function, which is negative x, times the derivative of the inside function. And the derivative of negative x is negative 1. And that's the derivative if x is less than 0. Now take a second look at that, though. When you take the negative 1 and you multiply it times the negative in the denominator of the fraction, those are going to become positive. So in other words, the derivative is the same regardless of whether x is greater than 0 or whether x is less than 0. So our conclusion is going to be that the derivative with respect to x of the natural log of the absolute value of x is always going to be equal to 1 over x, assuming x doesn't equal 0. So on any interval that doesn't contain 0, the derivative of the natural log of the absolute value of x is 1 over x. Okay, so now go back to the first question, the original question that we were trying to ask. How do we take the antiderivative of f of x equals 1 over x? What function do you start with whose derivative is 1 over x? Well, it's not just ln x. It's the natural log of the absolute value of x. So that's our conclusion. So for f of x equals 1 over x, the antiderivative is given by the natural log of the absolute value of x plus c on any interval that does not contain 0. So once we know that, we just apply all the other antiderivative rules that we have found. So for example, if we wanted to find the most general antiderivative for f of x equals e to the x plus 5 over 1 plus x squared plus x plus 1 over x. The e to the x is not going to be a problem when we go to find its antiderivative. It's the simplest one we've got. Its antiderivative is e to the x. For the 5 over 1 plus x squared, it might be easier to think of that as 5 times 1 over 1 plus x squared. Those are in fact the same thing, because then that allows me to leave the 5 out as a constant. I'm going to leave it right there. And then I just need the antiderivative of 1 over 1 plus x squared, and that is the antiderivative of that. It's going to be tangent inverse of x. For this last term, x plus 1 over x, we don't have a rule that allows us to find the antiderivative of a quotient. You cannot just take the antiderivative of the numerator separate from the denominator. So what I'm going to need to do is rewrite this. If you take this x and divide it into both terms in the numerator, you should get 1 plus 1 over x. We'll take the antiderivative of that instead. The antiderivative of 1 is x, and as we just discussed, the antiderivative of 1 over x is the natural log of the absolute value of x, and then we remember to add our arbitrary constant. Please do not forget that absolute value. It is important. And that's how we work with it.